So welcome back, my dear students. Today's class we are going to see the numericals for the design of shear in an RC structure. So first question, design an RC beam of size 400 mm by 650 mm subjected to a live load of 35 kN per meter over a span of 9 meter. Design the beam for shear. The main reinforcement provided are tension reinforcement 5 numbers 25 mm 5 and compression reinforcement 3 numbers 20 mm 5. Consider M25 grade concrete and Fe 415 grade steel. So you are given the design for the flexure is given, that is your moment design for moment is given. Now you need to design it for shear, that is the shear force coming on the beam has to be resisted by the beam. So we need to provide the shift is a requirement for shear reinforcement. We need to provide that shear reinforcement. So assume an effective cover of 50 mm, you will get 650 minus 50, that is you will get 600 mm. This is your effective depth, you will get it as 600 mm. And the calculation of the load, the live load is given as 35 kN per meter. So calculation of the dead load, the width is 0.4, depth is 0.65 per meter length, density is 25 kN per meter cube. You will get this dead load as 6.5 kN per meter. From there, the total load you will get it as 35 plus 6.5, that is 41.5 kN per meter. Factorizing for dead load and live load, that is the factor of safety is 1.5. You'll get 1.5 into 41.5, you'll get it as 62.25 kN per meter as the factored load. So factored shear force is equal to WL by 2. Considering this as a simply supported beam, now this is carrying a UDL of 62.25 kilonewton per meter. So if I am taking the shear force, it will be WL by 2. The shear force at the maximum. We will not consider for the critical section because at the critical section we will be at a distance of D from here. So there won't be any variation, but if it is safe in this, it will be definitely safe here also. So the factored shear force you will get it as WL by 2, that is 62.25 into 9 by 2, you will get nearly 280.125 kilonewton. So we need to design the beam for resisting a shear force of this much. So the nominal shear stress or the actual shear stress coming on the beam, that is tau V is equal to VU by BD, that is 280.125 into 10 raised to 3 divided by B is 400 and D, that is 600. You will get this value as 1.167 Newton per mm square. Now we need to check this value for tau C max. That is from table 20, you will get the value for tau C max for M25 grade concrete as 3.1 Newton per mm square. That is from table 20, tau C max for M25, you can read it, you will get this value as 3.1 Newton per mm square. That is your tau V value is less than tau C max, hence it is safe. Your tau V value is 1.167. Here the tau C maximum allowable value is 3.1 Newton per mm square, which means it is safe. Now the design shear strength of the concrete from table number 19, that is design shear strength of the concrete means tau C, that is the shear stress taken by the concrete and main reinforcement. You will get it from table number 19. That is in table number 19 you require the percentage of tension reinforcement, that is 100 AS by BD. That is 100 into, here there are 5 reinforcement at the tension side, so 5 into pi by 4 into 25 square divided by BD, you will get it as 1.02 percentage. So corresponding to 1.02 percentage, that is you have for 1 and your M25 grade concrete it is 0.64 and for 1.25 it is 0.07. So you need to find it for 1.02. Here we will do with linear interpolation, that is you have for 1 you have 0.64 from the table 19, you got it as 0.64, and for 1.25 you have 0.7. so if I take this value as x and this value as y, this y value will be 0.7 minus 0.64, 0.7 minus 0.64. So if I am considering the above triangle, if I am considering this triangle, it is similar triangle, so I could write x by y, x divided by y is equal to this distance, that is 1.02 minus 1, that is 0.02 divided by 1.25 minus 1, that is 0.25. I'll get the value for x as 4.8 into 10 raised to minus 3. So at the 1.02% percentage of reinforcement, the value for tau c is 0.64 plus x. That is up to from here to here it is 0.64 plus x. Now you know the value for x, so that tau c at 1.02% is 0.64 plus x. You will get it as 0.6448 Newton per mm square. That is shear force to be resisted by the concrete and main reinforcement. If I am denoting by VUC, then VUC is equal to tau C into BD. Here we got the value for tau C, and you will get B, no, you know the value, and D, you know the value as 600 into 10 raised to minus 3. In order to convert it to kilonewton, I will get it as 154.75 kilonewton. That is the shear force to be resisted by the concrete and main reinforcement. I will get it as 154.75 kilonewton. So here your value for tau V is 1.167 Newton per mm square, and your tau C value is 0.664. That is, your tau V is greater than tau C. Therefore, shear reinforcement need to be provided. That is, we will provide shear reinforcement in the form of vertical stirrups. So remaining shear force to be resisted by the shear reinforcement, if I am denoted by, we had denoted by VUS, VUS is equal to VU, that is the factored shear force minus design shear force of the concrete and main reinforcement, that is VUC. I will get it as 125.375 kilonewton. So that has to be resisted by the shear reinforcement. So consider two-legged 8 mm shear reinforcement. I will get the ASV, that is the area of shear reinforcement, as if I am like taking two-legged stirrup, then 2 into pi by 4 into 8 square. So page number 73 for vertical stirrups, you will get this value as VUS is equal to 0.87 FY divided by SV. You get this value as for two-legged 8 mm stirrup. You will get this spacing required as 0.87 FY by VUS. That is, you will get it as 173.7 mm. So the minimum shear reinforcement ASV by BSV must not be greater than or equal to 0.4 divided by 0.87 Fy. That is the maximum spacing. I'll get it as SV is equal to 0.87 into 415 into 100.4 divided by 0.4 into 400. That is 226 mm. That is the maximum spacing. I can denote it as 0.75D. That is 450 mm or 300 mm. So from this 4, there is 300 mm, 450 mm and 226 mm. These are the maximum spacing criteria, and our design spacing we got as 173.7 mm. So I will provide two-leg 8 mm at 170 mm center to center. Now the minimum shear reinforcement shall be provided in the center half. That is, in the center half portion, this value is VU. We have calculated the shear reinforcement for this particular value. Actually, when this span is going this way, the shear force value is decreasing, so that we don't require that much amount of shear reinforcement at this position. So what the code suggests is when VU is less than VUC, there is only minimum shear reinforcement required. So we will find the value. We know this value for VUC and we know the value for VU. We will find at what distance will this become VUC. So when I am calculating, this is a similar triangle. This is the half portion of your shear force diagram. I will get VU by VUC is equal to 4.4 divided by X. I will get the value for X as 2.48 meter. That is, this value for X is 2.48 meter. That is, I will get the value for Y as 2.01 meter. So what I do is I will provide the design shear force for this Y distance, that is up to 2.01. I will provide this value for shear reinforcement as two-legged 8 mm at 170 mm center to center, and further after 2.5 meter 2.01 meter the shear force is less than or equal to VUC. So there I will provide the minimum shear reinforcement, that is the minimum shear reinforcement is two-legged 8 mm at 225 mm center to center. Here you have seen the minimum shear reinforcement required is 225, because from here 225 to 26, this is 450 and 300. So the minimum or maximum spacing is corresponding to the minimum shear reinforcement is 225, rounded to 225 mm. So I will provide two-legged 8 mm at 225 mm center to center. I have the simply supported beam like this. The shear force diagram is coming in this way. This is your VU. At this point you will get VUC. This distance is 4.5 meter. So at this support I got the value for shear reinforcement as 2-legged 8 mm 5 at 170 mm center to center. So if I am drawing the tension reinforcement, that is at the bottom, and the compression reinforcement at the top, then up to a distance of 2.01 meter, that is your Y, and this is your 2.48 meter. 2.48 meter, that is your X. This is your X value, and this is your Y value. So up to Y, I had to provide 2-legged 8 mm at 170 mm center to center. I'll denote it by this green color. That is, I'm providing shear reinforcement like this. And this is 2-legged. And the other portion I could provide 2-legged 8 mm at 225 mm center to center. That is the minimum reinforcement required. I'll provide this this 2-legged 8 mm at 225 mm center to center. So similarly, you need to draw it for the other side also. So I hope you are clear with this design for shear. Now next problem we will see the design for shear when we are using bend up bar. So you can see the next question. An RCC beam of size 360 mm by 700 mm is used for a simply supported span of 8.4 meter. It is subjected to a live load of 65 kN per meter. Reinforcement used are tension reinforcement 8 numbers 25 mm 5 and compression reinforcement 4 numbers 25 mm 5. Design suitable shear reinforcement for the beam using bent up bars. Also use M20 grade concrete, and Fe415 stainless steel. Use limit state method. So you can see here, since the load is very much high, the tension reinforcement and the compression reinforcement are very much high. That is, this beam is heavily reinforced. You are asked to design it for the shear reinforcement using bent up bars. That is, we need to provide bent up bars for design of shear. As you know, the bent up bars the bent up bars are always provided along with the vertical or inclined shear reinforcement. If there is a need of shear reinforcement here, we need to provide using bent up bars as well as vertical shear reinforcement. So here we need to design using bent up bars. So what we generally do is we will bend the bars which is present at the tension side. So we can assume how many bars we need to bend. So here for starting, I'll assume let us bend 25 mm bars from the bottom. That is, there are 8 bars. Out of that we will bend 25 mm bars. That is the calculation of the load. The live load is given as 65 kN per meter. The dead load I will calculate as 0.36 by 0.70 by 1 into 25 kN per meter cube. That is 6.3 kN per meter. I will get the total load as 71.3 kN per meter. From there, the factored load, that is multiplying it by 1.05, I will get this value as 106.95 kN per meter. Calculating the factored shear force, that is your VU, I will get it as WL by 2, that is 106.95 into 8.4 divided by 2, I will get this value as 449.19 kilonewton. So for this value, we need to design for shear. That is, it is to be taken by the concrete, main reinforcement and if needed shear reinforcement. So the nominal shear stress or actual shear stress tau V I can calculate as tau V is equal to Vu by Bd, that is I will get it as 449.19 into 10 raised to 3 divided by 360 into 630, and taking this 630 because it's given, taking the value for effective cover as 70 mm. This is given 360 by 700 mm, and it is 8 numbers of 25 mm. So even if we calculate the value for approximately, if you are giving a 20 centimeter clear cover, then another 25 centimeter of main reinforcement, and half of that we need to provide 12.5, that is nearly it will come 62 point something. So I will provide a safer side, I will provide 70 mm cover. So this, the main reinforcement will be having a center of gravity at a distance of 70 mm from the bottom tension fiber, that is effective depth I will get it as 700 minus 70, that is 630 mm. There is a value for tau V, I will get it as Vu by Bd, that is 449.13 10 raised to 3 divided by 360 into D. Now I think you are clear, that is 630. I will get it as 1.98 Newton per mm square. That is from table 20, if I am calculating the value for tau C max, I will get this value as 2.8 Newton per mm square. That is tau V is less than tau C max, hence it is safe. Calculation of tau C, that is the design shear strength of the concrete, that is the shear stress taken by the main reinforcement and your concrete. I'll get from table number 19, 100 AS by BD, that is the percentage of tension reinforcement. I'll get it as 100 into, here there are actually 8 bars being provided at the tension side, out of which 2 bars are being bent up. So if I am taking at the, so if I am considering the end section, at the end there will be only, suppose this is my beam, now this section, there are 8 bars being provided at the bottom, and out of which 2 bars are bent up, so if I am taking a section at the support where I am calculating the shear force, there will be only 6 numbers of tension reinforcement. Will be only 6 numbers of tension reinforcement. So 100 AS by BD, the code has suggested AS means the area of tension reinforcement at the section considered. At the section considered, there are only 6 numbers of 25 mm bar. So I will take for 100 AS by BD, that is 100 into 6 into 25 square by 4 into pi divided by 360 into D, that is 630. I will get it as 1.3 percentage. That is from linear interpolation. For 1.25 it is 0.67 and 1.5 it is 0.72. I will consider this value as x and this value as y, and from linear interpolation I will get the value for x by y and x as 0.01. That is, I will get the value for tau C as x plus 0.67, that is 0.01 plus 0.67. This value I will get it as 0.68 Newton per mm square. That is, tau V is greater than tau C, which means I need to provide shear reinforcement to resist the shear which is coming on the beam. So provide shear reinforcement in the form of bend-up bars and vertical stirrups. We will provide the shear in the form of bend-up bars and vertical stirrups. That is, shear force to be resisted by the concrete and main reinforcement taken as VUC is equal to tau C into BD. I'll get the value for tau C as 0.68 from table number 19, and B into D I'll get this 154.224 kilonewton. That is, shear force to be resisted by the shear reinforcement VUS is given as 154.224 kilonewton. That is, the shear force to be resisted by the shear reinforcement VUS is equal to Vu, that is the shear force minus the shear force taken by the main reinforcement and concrete. I'll get it as 294.966 kilonewton. You need to take this much amount of shear. Now we will calculate the strength of the bend-up bars. That is, the strength of the bend-up bars, I can take it as VUS bent given in your IS 456 is ASB into 0.87 Fy into sine alpha. That is, ASB is the area of bend-up bars. There are 2 bars of 25 in diameter, that is 2 into pi by 4 into 25 square into 0.87 into Fy, that is 415 into sine alpha. That is, alpha will assume it as 45 degree. We are bending it as 45 degree. So I will get this value as 250.64 kilonewton. Now suppose if it is given you are bending 500 mm steel, 500 grade steel. Even though if you are taking 500 grade steel, you should restrict the value while designing to 415. That is, the code recommends doesn't recommend higher grade of steel for shear design. As the grade of steel increases, what happens is the carbon content will also increase, and as a result, it will become more brittle. When it becomes more brittle, what happens is that you are making the stirrup by bending it, and at that time you may not able to bend it properly because it has lost its ductility property, and as a result it won't bend properly. So the code restricts the use of Fe500 for shear design, even though that is, I'll take it as a note, in LSM, that is limit state method, Fy not greater than 450 Newton per mm square for shear reinforcement. We will not use Fy greater than 450 Newton per mm square for shear reinforcement. That is, if Fe 500 is provided, design shear force for a maximum of Fe 415 only. That is, while calculating the design shear force or shear for bend, we will take it as 415, even though if it is given as 500. So the vertical shear reinforcement shall be designed for VUS minus VUB, that is 294.966 minus VU, this is not VUB, I'll change it, this is VUS bend. So the vertical shear reinforcement shall be designed for VUS minus VUS bend, that is 294.966 minus 250.64, 44.326, or VUS by 2, that is 294 by 2, that is 147.483 kilonewton. That in this is given in the vertical shear reinforcement shall be designed for either VUS minus VUS bend, that is 294.966 minus 250.64, 44.326, or VUS by 2, that is 394.96 by 2, that is 147.483. The larger of this or the smaller of, we will design it for the larger of these two. That is, we will design a minimum of VUS by 2 for your main vertical reinforcement. That is, you can see in your code where bend-up bars are provided, their contribution towards shear reinforcement resistance shall not be more than half the total shear reinforcement. That is, it should not be more than half that of the total shear reinforcement. That is, you have the total shear reinforcement required as 294.966. So when you are providing bend-up bar, you should not use the bend-up bar for more than half of this. That is, minimum half of this should be taken by your shear reinforcement, that is your vertical bars, vertical stirrups. So from the close, I will take, we have to design for a maximum of 44.4326 or 147.483. So design the shear for 147.483. We need to design the shear reinforcement for 147.483, and the remaining will be taken by, out of this, actually the bend has a capacity for taking 250.64, but we will limit to the maximum of these two. That is, we will consider only the bend is taking 147.483. The remaining has to be taken by the shear reinforcement itself. That is, we will limit the value for limit the strength of this VUS bend to 147, and the remaining 147.483 has to be taken by the shear reinforcement, that is your vertical bars. So assuming 2-legged 8mm5, spacing of 2-legged 8mm5 for vertical shear reinforcement, I will get this equation as SV is equal to 0.87 Fy ASV D divided by VUS by 2. That is, VUS by 2 is 147.483. So I'll get this value as 0.87 into 415 into 2 into pi by 4 into 8 square. That is your 2-leg stirrup into 630 divided by 147.483. I'll get that value as 155.04 mm. That is the minimum shear reinforcement criteria you have. ASV by BSV must not be greater than 0.4 by 0.87 Fy. There you'll get the value for spacing maximum spacing as 252 mm, which is safe. This is 155, so it is okay. Now The maximum spacing criteria based on the bar diameter, that is 0.75d, that is 472.5 mm or 300 mm, which means we can provide a spacing of two-legged 8 mm 5 at 155 mm center to center. So this is 252, the other one is 472 and 300. So we will provide the design spacing of 155.04 mm. Suppose this designed spacing was more than this 252, then we should restrict to 252 mm. That is the criteria for minimum shear reinforcement. So provide two-legged 8 mm 5 at 150 mm center to center. This I have provided as 150 mm because that will be easy for when you are laying in the field. Rather than 155, this 150 will be easy. So we will stop for today's class here, and we will see the drawing for this question in a live session in the next class. Thank you and have a nice day.